Yes, Pawan, if you can confirm that I am audible and the screen is visible.
Yes, you are audible and screen is also visible.
Okay, thank you. So we'll start in another minute. Okay, so good noon, all of you. Uh, so I think the reason for keeping, one extra lecture on Wednesday up to NSEM is that we are somewhat lagging behind in terms of the required course coverage as well as if you compare it with the section B. The reason for us lagging behind is that maybe I am doing a few things in detail, or something, some things I am taking from other reference books as well. So in order to explain one concept, it takes at least 2 to 3 lectures. Secondly, I have to write down also, so this is also one of the things. But anyways, I hope that with 3 extra lectures or 4 extra lectures at max, we would complete what is required. So today I will start from where I left yesterday. So we were discussing Gaussian random variables. Basically, we are not discussing; we are revising because I hope that you have gone through it in the probability course. But because we need it a lot, so we should revise it. So today we will start with the concept of multiple Gaussian random variables. Okay, or first let us start with multiple random variables. Okay, multiple random variables. How to study? Okay, this is the question you would answer, because ultimately we need to study multiple Gaussian random variables. Now, what is the motivation for studying multiple Gaussian random variables? Basically, if you take the noise process n of t, that is, this is the a wide Gaussian noise process, so you will sample it. Basically, you will sample it and then study it. So once you sample it, so this leads to a vector of, this leads to this leads to a vector of Gaussian random variables. Okay. So we must know how do you study a vector of Gaussian random variables or multiple random variables. The same thing. Okay. Just you stack together multiple random variables and you will get a vector of random variables. So this is the motivation. We need to know how do you deal with the vector of Gaussian random variables. Okay. So let us start with first of all the study of multiple random variables. So consider an arbitrary m dimensional. Arbitrary means that it has no structure fixed there or no property. Right now we are not specifying any property. So we have considering an m dimensional random vector, which is denoted as x is equal to x1, x2, and this goes up to xm. Then you have a transpose operator here. It means that it is a column vector, basically a column vector. Okay. Define n cross 1 mean vector. Okay, by taking the ensemble average of each of the elements of the vector of x as, so we may use a notation like this also to represent that this is a vector, but during writing of whatever I am saying, it may happen that this bar or this under bar gets ignored, so it should be clear from the context that we are talking about vector as m of x bar, which is equal to, you take an expectation and you put this operator, expectation operator, over this column vector. So the way to do is it, yes, take this expectation to each of the elements. Okay, so this is defined like this: expectation of x1, expectation of x2, and this goes on. This is expectation of x of m. Okay, and then you take this transpose. I think I should use this bracket as a curly one only. So this is the way you will define the mean vector. That is, you just take the expectation of each of the elements. So this results into another column vector, but this is not now random. These are numbers. Okay, this is the mean of each of the random variable in the random vector. Okay. Now also define M cross M covariance matrix. Okay. Covariance matrix of X as, okay, let us define this. This is the element of this matrix, ith and jth element, I comma jth element is defined like this. It gives you the covariance of xi and xj. Okay, they are the two members of this vector x under bar. Okay, so how to define that? I think you know it, that this is given by expectation of xi minus the mean of xi into xj minus expectation of x of j. Okay, I think you must have gone through this covariance. This will tell you whether the two random variables are correlated or uncorrelated. If they are correlated, then you can obtain the coefficient of correlation as well. Okay, so this, if you solve, so this you will get, I think this solution is quite easy, so I am not doing it. This is xi xj minus the product of the individual means. Okay, or you can say the ensemble averages. So with this as the definition of the ijth element of this covariance matrix C of x bar under bar, we can say that C of x bar is nothing. This is defined like this: x bar minus expectation of x bar into, now you will have to use a transpose operator because this transpose. Okay, now you can see what is this. This is m cross 1 and what is this 1 cross 1. Okay, so this gives you a m cross m matrix, and following the reduction above that is said in 1, we get that this is same as expectation of the transpose. See, right now we are assuming that elements are real. Elements in x bar are real. Okay. Otherwise, what will happen is that you will have to use a Hermitian operator. And what will Hermitian do? In addition to taking the transpose, it will conjugate each of the elements of x bar. That is the way over these spaces this covariance is defined. So we are not going into that. That how do you do that? Because that has to be done in a separate course. Either you can do like this, or you can do like this also. You can write this as this expectation of x bar and whole transpose. Okay, so this is what, this is m cross 1, 1 cross m, so this is m cross m, and this is what, this is m cross 1. Similarly, this is 1 cross m, this is m cross m. So subtraction of two m cross m matrices, this will give you m cross m matrix. Okay, so this is what is the definition of the covariance matrix for a general random vector. I have not yet specified that what are x1, x2 and xm. Okay, so now we will define the coefficient of correlation or correlation coefficient. So what is the correlation coefficient? So between two random variables. See, I am right now not specifying that these random variables have to be defined over a common probability space. Okay, this I have somewhat eliminated because I don't want to enter into being very specific about these things, because whatever we would be doing in our course, so those random variables would satisfy these things, that they are defined over a common probability space and everything. So I don't want to make this course as a subset of a probability course. I am making whatever I am doing as an application of what we have learned. Okay, so I am not being very specific about few conditions. So this, whatever I am doing, should not be treated as a fundamental introduction to these things. This is a sort of a revision, okay, which might omit few of important details. Assuming that you might be knowing it, or you, when you will go back and study from the standard text, you will get to know it. Okay, so between random variables x1 and x2, is defined as, I think this also you must have seen, you denote it as this is rho of x1 comma x2. This is the correlation coefficient. One important thing about correlation coefficient is that it is a dimensionless quantity. Okay, let us see how. So this is defined as covariance x1 comma x2. Not dimension, I think this is scale independent. Yeah, right? In the root of variance of x1 into variance of x2. Okay. So what is variance of x1 and x2 or variance of xi? This is quite simply you can obtain like this. So variance of xi. If I talk to you about it, if you recall, this is nothing but the expectation of this square. Okay. This is nothing but saying this is the covariance of xi with itself. Okay. So you can check what is the covariance. We defined that between I and j it is expectation of xi minus exi into xj minus expectation of xj. So if you put j as I, so this becomes a square, and that is what we have learned, that the variance is nothing but the second moment of this scaled random variable or zero mean random variable. Now what is this? This is a zero mean random variable. Okay? Because what we have done, we have taken the random variable and subtracted the mean. So this new random variable will have a zero mean. So the second moment of this zero mean random variable is the variance. So this can be easily written like this. Okay. Okay, so correlation coefficient, because it has been scaled by the variances, you can say that it is a scale independent. This is correlation coefficient, I should write like this. So CC, it is a scale independent measure of the correlation between two random variables. Why do we say that? Because covariance also gives you the same, but we have not yet scaled it by the individual variances. Okay. Once we scale them by the individual variances, this becomes a scale independent, okay, quantity. I am not throwing much light on it, but you may just feel intuitively, because we do not have that much time to prove it, but you can assume that why covariance we cannot take it as a measure of correlation. Okay, but we want a quantity which doesn't get scaled because of a change in the variances. Okay, so that is what we have done. We've just scaled it by the variances. Now, few properties which are important. Few properties of the covariance matrix or covariance in general is, so covariance is unaffected by adding constants. Okay, this must be known. Why? Because covariance already subtracts the mean. That is, let us see what I mean. That the covariance of x plus a and y plus b. Suppose x and y are two random variables, a and b are two scalars. So this is same as covariance of x comma y. Okay, for any constants a comma b. Okay, so x and y are random variables. X comma y are random variables. Okay. Why this happens? Because covariance provides a measure of the correlation between random variables after. So this is a measure of correlation, but this is a correlation coefficient. So slight difference. The difference is you scale by the variances. Okay. Anyways, after subtracting out their means. Okay. Now what does this mean is, see, if you add a constant to a random variable, so what change it will give? Only the mean gets scaled or shifted. Okay, variance in every other thing remains same. So addition of a constant to a random variable changes the mean. Once you, because while defining covariance, you will always subtract the mean. So the change which has happened because of adding a constant is already subtracted out. So you land up with the covariance which is of the random variables when there was no addition of any constant. Okay. Hence adding constants to the random variables does not, which basically, let me write it down, which changes their mean, does not affect covariance. Okay. Now one property is that is one use of the above property. See why will we use it? Where will we use it is, suppose y is equal to small x plus x. Okay, where s is a, because such signals will definitely be there when we will do the detector. Okay, so that's why we are taking an example from what we will use. So S is a where S is a deterministic term. S is a deterministic term. And X is a zero mean random term. Okay. You can say random term or random variable, random process. So the use is, in order to compute covariance of y, it is convenient to drop this. Okay, so suppose you have a model in which you can clearly see that there is a deterministic term and you know what that term is, which adds to the random term to generate y. You can simply drop that and simply obtain the covariance of x only, which will be the covariance of y. So covariance of y is not at all dependent upon this deterministic addition, okay, or this deterministic term which adds to the random part. Okay, to drop this. This example may not be very proper because we have not yet discussed a scenario in which this will happen, but to be used later, you can say a faint memory of this, that okay, if by chance this will happen, then we can simply work with the covariance of x, which will directly be equal to the covariance of y. So deterministic terms which will add to the random terms doesn't impact the covariance. Okay, so we can say that the covariance of the random term is preserved even after adding constants. Okay, that won't change. Now let us define a few more things. So for a random vector x under bar, which is m cross 1, let us define another random vector, which is, that is the way we obtain a x bar plus b. Okay, where this is a matrix. This is suppose an n cross m matrix. This is already m cross 1. This has to be n cross 1. And this will be ultimately n cross 1. Okay, so we do a linear transformation. Okay, or you can say an affine transformation. So what will be the mean and the covariance of phi? That is what we are interested in, because you will see that this x, if at all this represents the transmitted information, let us say in the case of multiple antenna and everything, so you receive a y vector. So you have to deal with y. So you are interested then in obtaining the mean and variance of phi. And if at all you are given that what is the mean and variance of x, so how do you obtain the mean and variance of phi? That is the you can say in the study of interest. So we will be doing that. So what will be the mean m of y bar? So this will be simply expectation of y underscore or under bar, you can say. This is equal to expectation of where you Must remember that A and B are deterministic, they are not random. Right now we are assuming that A and B are known to us. Okay. So this, then in that case, this A will come out and the expectation, although expectation is linear operator. So this I should write it down so that this is very clear. Okay. What I mean to say is that this is equal to expectation of A, because expectation is a linear operator. So this distributes like this. Now since B and A are deterministic, so you will have like this plus B bar. Okay. Let me write it down. A and B are known and deterministic. Okay. So this is nothing but A times mx bar plus b. So it's easy to see that the mean of y can be easily expressed in terms of mean of x if you know A and B. Okay. Then let us try obtaining the covariance of y. So this is given as expectation of y minus expectation of y under r into y bar minus expectation of y bar transpose. Okay. So you just plug in the expression for y and y bar. So you will get that this is equal to expectation of A times x minus mx into x minus mx transpose A transpose. Okay. So this is equal to A times Cx bar A transpose. Okay. So you will see that the covariance of y, we have already seen that addition of constant doesn't affect it. So you see that in the ultimate expression for the covariance of y, there is no mention of b. A will definitely impact it because A will impact the variance as well. You might know that the multiplicative thing, that is, if x is a random variable, then A times x will scale the mean as well as it will scale the variance also. So you will find this, that this is present. Okay, so A Cx A transpose is the ultimate, then say the expression for the covariance of y. So we note, so you can note. See, such expression arises in communication systems a lot. Y is equal to Ax plus B. That's why we are studying this model. Okay, this is one of the fundamental models over which communication systems are modeled, and then we design detectors based on the assumption that our received vector follows this. Okay, and X will be the transmitted vector. B will be some sort of a noise. A will be some sort of a channel. Okay, so that's why we are studying Y is equal to Ax plus B. And you will find maybe in few textbooks this derivation will be given, but in others it will be assumed that it is quite easy to see that the mean is this and variance, covariance will be this. Okay. So note that mean of y, right, depends only on the mean of x, and the covariance of y depends on the covariance of x, depends upon the covariance of x. Okay. And I must write that additive constant vector p does not affect covariance since it only influences the mean of y. Okay, this we have already seen in the case of random variables. So with this as the background, let us now introduce the concept of joint Gaussian random variables. Okay. first. So when do we call, let us say, a set of variables as jointly Gaussian? So this is very important because this joint Gaussian word or a Gaussian random vector or a Gaussian random process you will encounter 99% of times in the design of communication systems. Now, by communication systems, I would say up to 4G at least. Okay, it means 1G, 2G, 3G, 4G, they all basically struggle with, you can say, Gaussian random vectors, jointly Gaussian random variables, and Gaussian random processes because most of the thermal noise is modeled like through a Gaussian white noise process. Okay. And the Shannon's theorems also, or the theorems of information theory, assume that what you can, if at all you transmit anything which is Gaussian distributed, you will achieve the capacity. Okay, so that's why this category of random variables, Gaussian, that is Gaussian, holds value for us. Okay, so we should know when do we call a set of random variables as Gaussian. Okay, so you will find this written at several places, jointly Gaussian, but we should know, no? So that's why we are studying this before we move with the ultimate detector design. So the m cross 1 vector, the m cross 1 vector, random vector, x bar, which is equal to that I have already written above, but let us write it for the sake of completion, is termed a Gaussian, is termed a Gaussian random vector if any, this is very important, if any linear combination of these random variables is a Gaussian random variable. Okay, this is important. It means, let us say you are given a vector which has m cross 1 entries, or you can say its size is m cross n. It has m, you can say, variables, random variables. So if you take any linear combination of them, so if you take a linear combination of them, you will obtain a random variable. So that random variable must be Gaussian. If this happens, then you will call that these random, or the x will be a Gaussian random vector, or x1, x2, xm are jointly Gaussian random variables. Let us take, to be specific, for any scalar or any scalar constants. So I have not said that they have to be positive or negative, they can be anything, they have to be scalar constants, a1, a2 up to am. The random variable, which is a1 x1 plus a2, or I should write capital instead of small because otherwise it will lead to confusion. This has to be a1 x1 plus a2 x2. This is a random variable basically. am xm is Gaussian. Okay. So this must be known that for any, if this holds, this is important, I am putting it in inverted commas, that for any choice of a1, a2, am, if you take this linear combination, this should always give you a Gaussian random variable. Then you will call that this is a Gaussian random vector, or you can call it to be you can call x1, x2, xm to be jointly Gaussian random variables. Okay, so this must be known. Now, this is important. So a Gaussian random vector. Now, by saying Gaussian random vector, it means that the random variables, any linear combination would lead to a Gaussian random variable. Okay. So Gaussian random vector is completely characterized. By its mean. This is important to understand. By its mean vector and covariance matrix. It means you do not need anything else to completely characterize the statistical behavior of a Gaussian random vector. Why is it so? Let us see this. Okay, ये Gaussian के बारे में यही बहुत अच्छी बात है कि आपको अगर if you talk of a Gaussian random variable, then you have seen that the PDF in order to obtain the PDF you only need two moments. That is the first moment and the second moment, or you need the mean and the variance. The same behavior is displayed or is observed in Gaussian random vectors also. You need only two things. One is the mean vector and the covariance matrix in order to specify the statistics for a Gaussian random vector. You do not need higher order moments, okay, or anything else. So let us see why this happens. So for x bar equal to x1, x2 up to xm transpose, consider y is equal to, so this y is a random variable now, a to x2 plus up to plus am x, so just rub and so consider y which is equal to a1 x1 plus a2 x2 plus up to am xm, okay, where a1 a2 up to am are any scalar constants. I have repeated so that if you read this point 1 as a standalone thing, you know what we are doing. Okay. Now, since you must know that since y is a Gaussian random variable, because we have said that x is a Gaussian random vector variable and is completely you know that if at all this is a random Gaussian random variable, it is completely characterized by its mean and variance. Okay, so you just need two things of this random variable. We can compute these as, it means in order to specify y we need its mean and variance, so that has to come in terms of the mean and variances of x1 and xi's. Let us see how does this happen. So we note that as first let us say note that y can be written as A transpose x bar, where what is A bar? That is now a row vector. Okay, I am not using a transpose here because this will be a row vector. Oh, sorry, this has to be a transpose. Yeah. So once you take another transpose, this becomes a row vector. So this is a row vector, this is a column vector. So this then leads to a scalar. So this is what? This is 1 cross m, and this is m cross 1, and this leads to a 1 cross 1 number, or you can say a variable. Okay. So what is m of y? M of y is nothing but A transpose m of x bar. So this is what? 1 cross m. This is m cross 1. Okay. And what is C of y? Which is covariance of y, or this is nothing but variance of y. Because covariance is what? I have seen, I think written it above, that covariance of y of any random variable is simply the variance of that. This is equal to A transpose C of x bar A. Okay, so let us see what is it. This was m cross m, this is m cross 1, and this is 1 cross m. So what is it? This will lead to a m cross 1 vector. Okay, and this 1 cross m multiplied by m cross n would lead to a 1 cross 1 number. So my and cy, they are both 1 cross 1, or you can say that they are scalars. So in terms of the mean vector of x and in terms of the covariance matrix of x, we can find the mean and variance of any y. Why I am saying any y? Because we have said that a1, a2, am are arbitrary. So for any arbitrary combination, the random variable which I obtain is completely characterized in terms of the mean vector of x and the covariance vectors of x. So you can say that, so this implies that in order to specify the statistical behavior of x bar, we only need these two. One is vector mx and the matrix cx bar. Okay. So I am writing it down whatever I have said. So we see that once we know mx bar and cx bar, the density of an arbitrarily chosen linear combination this has to be linear combination y can be known or you can say developed. Okay. So one more important thing to write here is, so definition. So if at all you have anything to ask or comment upon, you can just unmute and say. See, this topic will help you a lot in other courses as well, because you will encounter Gaussian random vectors at several places, and we generally say it is a Gaussian random vector, but we do not know what do we mean by it. So जो दिमाग में सबसे पहले आता है कि each of the element is a Gaussian random variable. See, that doesn't prove or show that it will be a jointly Gaussian random vector or variable. Sorry, it will be a Gaussian random vector. मतलब सबसे पहले मीनिंग अगर आपको बोला जाए कि it is a Gaussian random vector, so what you will straightforwardly imply is that x1, x2 up to xm, each of them is a Gaussian random variable. So this is what comes to our mind, and maybe a lot of you must be assuming that this is the definition. No, this is one of the part of the definition. The second part is that every linear combination, which is the most important thing, every linear combination must give you a Gaussian random variable. Okay, this may not be satisfied in a few cases, which we will see. Okay, so that is what I think I wanted to highlight, that if we do not go somewhat deeper in the definitions, we might be assuming something faulty or incorrect or incomplete. And once we really encounter problems in which we have to solve something new, it means suppose we encounter research problems, then we see that we are committing a mistake or our definition lacks rigor. So whenever we are going to study these things, we should study somewhat properly. So that is what we are doing. So the definition of joint Gaussianity only requires us to characterize the distribution of the arbitrarily chosen linear combination of x1 up to xm. Okay, so by the logic above, we can say the distribution of Gaussian random vector X is completely characterized by mx and Cx bar. Okay, so what do we say is, so the definition of joint Gaussianity only requires us to characterize the distribution of the arbitrarily chosen linear combination of. That is what I think we have written above, that for any scalars even up to am, this has to be a Gaussian random variable. Okay, the linear combination. Whatever random variable you get should be Gaussian. So in order to really check or specify, or you can say define X bar, you only need the PDFs of the the random variables which are obtained by the linear combinations. For that, we know that we only need M of X bar and C of Y bar, or sorry, C of X bar. So this is what we written. The definition of joint Gaussianity only requires us to characterize the distribution of the arbitrarily chosen linear combination. So by the logic above, that is the logic which we have just derived, we can say the distribution of Gaussian random vector is completely characterized by mx and cx. Okay. So this is not a very, you can say, rigorous statement, but at the level at which we want to study Gaussian random vectors, this will suffice. Okay. Means this is some sort of a logical way of saying this. Okay, logical way. Why? Because we have derived it from the definition. So that will work for us as of now. Okay. So what is the notation? So let us now come to the notation point, that how do you write down that some vector is a Gaussian random vector. The notation is, you write like this. This is normally distributed with mean and covariance C. Okay. So this denotes, you can say, denotes a Gaussian random vector with mean vector with mean vector M bar and covariance matrix C. So those who have gone through few research papers, they might they can relate that there it is written that if at all you have a relative white Gaussian noise vector, this is distributed like this: 0 comma sigma square into I. Okay. So this means that this will be a zero vector, so it is a zero mean. Each of the element has a zero mean of this n. Suppose this is n cross 1. Okay. And the covariance is an identity matrix. Now what is the meaning of this? This is like this: sigma square 0 0 0 sigma square and then finally sigma square. So this is an n cross n matrix. So if at all you have gone through a few research papers based on multiple antenna technology, or at other places also, maybe in the domain of coding also, if at all you have done some project work in introduction to communication systems, there you might have encountered this. So the theory behind this is what we have done above. Okay, so this was important for us to study. Otherwise, if we try to do some research work later on, we might commit some mistake because of our loose understanding of it. Okay, so let us, I think I wanted to do one example where the joint density is not well defined. Let us not do that. Let us move ahead because we do not have that much of time. So let us now do, so in general, okay, I should not do that. This is another part. See, what I wanted to do through an example is that existence of density, you cannot confirm that always a density would exist. So let me do that. That will be. Let us take an example. Okay. So suppose you are given x1 and another random variable which is obtained from x1 like twice of x1 minus 3. Okay. So you have to check. So you have to check if they are jointly Gaussian. Suppose you are given that x1 and x, so x1 is a Gaussian random variable. So you know that you are just scaling it and subtracting a constant. So x2 will also be a Gaussian random variable. You have to check if x1 and x2 are jointly Gaussian or not. So for it, the standard check is that you will consider their arbitrary combination, which is, let us say, a1 x1 plus a2 x2, where a1 and a2 are arbitrary. They can be either positive, negative, but yes, they have to be scalars and they are fixed numbers. So you will obtain that this is a1 x1 plus a2 times twice of x1 minus thrice of a2. So this will lead to a1 plus twice of a1, sorry, a1 plus twice of a2 twice of a2 into x1 minus thrice of a2. Now what it is, so this is, if you know that x1 is a Gaussian random variable, you're just simply scaling it and you're subtracting a constant, so this remains to be a Gaussian random variable. So for any a1, a2, you can say that y will be a Gaussian. Y will be Gaussian. So you know that if I am just simply obtaining another random variable through this sort of an affine transformation on x1, I will land up with a random variable, and this random variable and the original random variable, they will be jointly Gaussian. Okay, so we can say will be Gaussian. Hence, x1 and x2 will be jointly Gaussian. But the question is whether the density, the PDF, will exist or not. So you will see that it doesn't exist. Why? Because another random variable can be directly obtained if you know x1. Okay. So on the x2 space, it means if at all I am drawing this, sorry, let me write it down. So question is the joint density well defined? So the answer is no. See, if at all you talk of the joint density, then on this plane of x1 and x2, your PDF must be, you can say, you can define over it. But the problem is your x2 is, you will have a line because x2 is directly, you can obtain from x1. So for any value of x2, you can obtain an x1, or you can say that all of x2 will lie across a line. Okay. So this leads to a problem. Let me write it down what it means. So in the 2D plane, I am not explaining that much, but this is just to highlight that vectors can be jointly Gaussian, but density may not exist in all the cases. Why? Because before defining the density of a random vector, we must know that where the inverse of covariance exists or not. I will do it. You can just sit back and see what we're doing. So in the 2D plane, all of the probability mass is collapsed onto the line okay. So one thing is this. So I am not specifying. Basically, you require delta functions in this case, but I am not going into it that if this happens, why the density cannot be defined. Instead, I am writing a simple explanation. The simple explanation is, since x2 is completely determined by x1, any probability involving an x1 and x2 can be expressed in terms of x1 alone. So what do we mean? So if you are given probability that x1 is 2, comma x2 is 4, okay. So what it means that This is simply saying the probability that x1 is 2, but this is not defined because x2 is 4 is not defined. x2 has to be from this expression. So this is 4 minus 3 is 1. So this takes up particular, this is 0. Why? Because x2 is equal to 4 cannot, x2 cannot take a value 4 if x1 is 2. But here this will give you a non-zero value, and this is same as saying probability that x1 is equal to 2. Okay. Let me not write equality here. These are two cases. This is case 1, this is case 2. Okay. So either it is 0 or it can be expressed in terms of the probability what x1 takes. Okay. It means in terms of the probability of the random variable x1. So in such cases, this joint density cannot be defined. Okay. P of x1 comma x2 cannot be defined. Cannot be well defined. Why? Because there is a sort of correlatedness or dependence among the two random variables, and this dependence is somewhat deterministic, or it is a direct relation. One can be obtained in terms of the other. Okay. If at all you have some randomness, if suppose x2 is twice of x1 plus x3, in that case the joint density may exist because they are correlated, but they are not directly dependent. Okay. It means one cannot be obtained easily in terms of the other. There is no deterministic relationship. Okay. So the fact which I wanted to highlight, I will write it down. So in general, so for you right now going deeper into this is not required. Only you need to know what I am writing. That in general, vectors can be jointly Gaussian, but density may or may not exist. And if it exists, so in what conditions it will exist? So I am writing it down. So in general, I think we are just moving towards the last part of random processes. It means introduction to random processes, what we wanted to do. Immediately after this, we will shift to the match filter, correlation receiver, and then finally the modulation schemes. Okay. So at that point, the course would end. So in general, when the m dimensional the joint density does not exist, probability involving x1, x2 up to xm can be expressed in terms of a smaller number of random variables that we have seen above and can be evaluated using a joint density over a lower dimensional space. And the conclusion of this is that joint Gaussian density exists if and only if and only if the covariance matrix is invertible. This is important. The covariance matrix is invertible. Okay, this is very much important to understand. Okay, and this is given as, so let me write it down. So for x is equal to x1, x2, and this going to xm, if it is distributed like this, m comma c, if c is invertible, the joint density exists and takes the following form. Takes the, I think you must have seen this. I will be writing it. This PDF you must have seen earlier. So this is the way to write the joint PDF or the PDF of the vector. So this you can write like this also. Okay, I should not write it like this. This is fine. A joint PDF is given like this. That is P of x bar, which is equal to 1 upon root of 2 pi to the power of m, the determinant of the covariance matrix. Okay, and this is e raised to power minus 1 by 2 x bar minus m bar transpose C inverse x bar minus m bar. Okay, so this clearly says that if at all the covariance matrix of these random variables, if at all that is invertible, you will have a density. If it is not invertible, then you cannot have a density. If it is not invertible, it means that one or other random variable is dependent on others, and you can basically remove it if you need to statistically characterize this set of random variables. Okay, that is what we have written above. Okay, so I think we are not interested in deriving this. We should know this, that if at all you are given a Gaussian random vector, how do you write its PDF or probability? Okay, so this gives you that probability that this is a density. Okay, so one important concept which I wanted to discuss is that of uncorrelatedness. This is the last concept for today. So this is what we should know. Correlatedness. So for two random variables x1 and x2 are uncorrelated. If covariance of x1 comma x2 is equal to 0. Okay. Now, one important thing, that if x1 and x2 are independent, I think this fact feature you must be knowing, but I'm just repeating it. Covariance of x1 comma x2, which is simply expectation of x1 into x2, that is a product minus. Now we know that if x1 and x2 are independent, this is same as saying that this gives you 0. Okay. And the important fact which I wanted to write down is independent random variables, independent random variables are uncorrelated, but converse is not true. This must be remembered. Okay, but there is an exception. Gaussian random variables. Okay, it means if Gaussian random variables are uncorrelated, they are independent. Okay, so it means converse holds. Okay, Gaussian random variables, or I should write not Gaussian, they should be jointly Gaussian. Let me write it down more properly, because this might lead to some confusion. So the exception is but does hold when the random variables are jointly Gaussian. Okay, so this is, you can say, you must remember, this is sometimes asked in interviews also, or if at all you are searching for jobs in the communication industry, this is the fact that you must know. So this is what I wanted to do for today. I think from next class, that is on Friday, we would start with the match filter design, or we would talk something about the noise process and T, and then we would start with the match filter design. Okay, so we are